to give half-understandable talks. Well, actually, they asked for 3, and then in the last I can go more wild. But I guess we agreed in the end on 2.5. So there should be still about half a lecture, as elementary as before. And then, so instead of making it complicated, I will just make a quantum leap. Go into a hyperspace, and will just completely disappear, and then I will just get out, bloop, on the other end of the tunnel. So there will be some, if you did notice something, maybe you will notice that I disappear into a sparkling point, and then I reappear again. But don't be surprised, because there will be some big piece missing there, because it's kind of hard to tell too fast. So I'll just skip it all. All right, so last time we talked about an infinite dimensional analog of this Gaussian integration. And let me just remind you what the main objects were. So if I consider potential u of phi, the potential, then we can consider partition functions at u, which would be then integral over d phi, which is that path integral of the exponent. And here we will have again some quadratic part, phi k phi. So this means, in fact, that there's double integral dx y phi x k of x y phi y. But I'll write it like that in the short notation. And then to this we add now some potential. Did I close on that? So, and then, yeah, I guess that's almost all I need here. So just to say that we've seen, more or less, that then it is given by z naught exponent of u, where now instead of phi, I substitute dj of some x, and this operator acts now on the exponent of all this, forget this stuff, g minus g equals 0, and here this g which appeared is the inverse of k. So again, when I write here u of phi, usually it has the form integral over dx u of phi of x. Some kind of thing like that. And then finally, well, do I want to? Yeah, I guess not. And another important object was the correlation function. Hmm? It can be anything. Sure. Yeah.
So the u downstairs.
This u downstairs. No, it stands for this very u.
Oh, on the next line.
One of the anagrams.
Here, this. Jesus, you didn't come another u?
No,
That doesn't matter. I mean, if you try to understand it by saying you mean the same u.
Well, it's the same u.
But the one
Not
up on
talking
top.
about the same- we're not talking about the same pair of views.
Up at the first line. Then you just put it there. Right at the end of the first line.
Ah,
You integrate. It's not, it's sort of the same.
it's not, yes.
It's a
It's not
code.
the logo,
Oh,
but
it's
the
the same
same
thing.
Sort of the same.
I agree, yes. Yes, and this
Other
is
than
it.
you.
Now, whenever I'm given several functions of phi, or rather, okay, let me do it for the coordinate functions. It's simpler. So if I have the coordinate functions, kind of the fields phi in point z1, etc., phi point zm, then we do the same, so we just plug. Now, the only new thing to do is to take the same exponent, phi plus u phi. But now also to plug in the integrand, the product of these functions. So right here, phi of z1 times etc. phi of zm. I should normalize it by subdividing by 1 over zu. And just to, here I denoted by u to see that here u is present, the potential is present here in the exponent. So this is the correlation function, and then assume that it can be written, finally as, what should it be, z naught over zu d dj z1 zm, and then there's only separator the exponent of u over jx. All these acting here on the exponent of j, and evaluated at g. So it's precisely the same formula as in the finite dimensional case. So, and then of course by the Weeks theorem I can do the same things as again we did in the finite dimensional case. So I can say that it is by Weeks theorem I can write as a sum over all pairings. So there will be again the sum of overall graphs. And then there will be some stuff, the type of the graph, or rather what I put in the vertices there will depend on this u. So we've seen in the example then that if I just take phi cube theory, then so that u of phi is the integral over dx of phi of x cubed. Then the graphs which will appear will be trivalent. So I will have some trivalent vertices in there. Now each vertex will be labeled by some point x, and I should integrate over this position of this vertex x always. This is instead of the summation which I had before over the labels of all these edges. And there will be also, of course, external legs. The external legs will labeled by this Z1. So the graphs will look like that. There will be some legs colored by Z1 and Z2, etc. up to Zm. And here inside there will be trivalent graph. So the rest of the vertices are trivalent. They correspond to this potential, cubic potential.
So if the potential is quartic, if the potential is quartic,
So if let's see. What would happen if I would take phi some other stuff, right? That's what you want.
Yeah, fourth order.
Okay, say fourth. Dx phi fourth. What kind of things am I supposed to get? So let's see. Let me just write again the same thing, only now already with this potential. So then the partition function. Let me just do an example of some, say, partition function of 2-point function, say phi of Z1, phi of Z2. So what will it be? So I just rewrite this formula above here. So Z0, ZU, D, J, Z1, D, J, Z2, and then I have the exponent of integral over dx, and here there's D, J of x, the fourth power. All this is applied to exponent J, G, J, and then we want to compute it in J equal to 0. And then I should write this exponent in the power series. So I'll have a lot of graphs. Oh, maybe you know what? Let me squeeze in some H so that it's easy for me to explain in terms of which order would I like to take. So let's compute the terms which would correspond to taking in the exponent just this part, okay? Just in the fourth. Because there will be, of course, a lot of things when I will write the expansion in the power series. So let's compute the terms corresponding to just this thing in the fourth. So it means that I have 6 derivatives. So I will have ddjz1, ddjz2. Let me interchange maybe the order of the derivative and the integral here, and then I will just write it as the integral over dx, which I will write outside. Again, z0 over zu. Oops, sorry, that is small. And then dj of x, the fourth. So all this stuff will be applied to x, j, g, j, j. So let's see how can we rewrite it using the same Wick's theorem. By the Wick's theorem, it should be the sum of all pairings of what? So all pairings of, here I will draw some big star, say, so it should be, we have 6 points here. I have 6 derivatives. Now, 2 of them have these labels Z1 and Z2. And the other 4, these 4 derivatives, are labeled by the same x. So I should take all pairings of these points. Whenever I have a pairing, I will write, so let me show what we do. So whenever I have some pairing, then what corresponds to this pairing of these 6 points? Well, I can also, let me just write the answer first of all, so it will be G of Z1 x. This is what I should put on the first page of this final diagram. Then there will be G of Z2x. Yes, this is now the second page. So this is this. This goes here. And then you can already guess what will be the last one. It's this. Now, I should also remember before I had to sum over all internal indices, which now means the internal index now is this x, right? So I'm now doing this integration over x. Integral dx. So to such a pairing, there corresponds this term. Now the same pairing I can draw somewhat nicing as a diagram if I just do it like that. I will draw the same 2 points, say 2 legs, again, labeled by Z1 and Z2. And here all these 4, since this is basically the same point, I will just draw it as one thick point, and this will be the graph, which I get, right? Yes, of course. Obviously, if we started from find the 4th, it will be 4 valent, just the same way as when we were with phi cube and we got trivalent. So this will be this graph. Now, so again, there will be the question whether there is also a graph which will look like that. Z1, Z2, and what can I do? Oh, okay, in the first order I don't have anything, but if I will now go to high orders, okay, so in high orders, in the higher loop configuration.
It's already a vacuum bubble with that one.
Higher loop contribution. So let's see what should be the next one. This will be, the next one will be when I'll have already more, when I'll have, say, 8 of these guys, right? 9, 10. So the important thing is that then these 2 loops, so what will be the graphs which will appear there? So there will be, again, instead of these 4 axes, there will be 4 x's and 4 y's. So, because when I will write the exponent, you know, the first terms of the exponent will be 1 plus, and then there's integral dx, and then this guy djx in the 4th, and then there will be half of integral dx dy djx in the 4th, djy also in the 4th, right? Plus, okay. This will be the second term of the exponent. It's a product of 2 integrals.
So what is g of xx?
Well, they may be extremely badly defined. Right? It can all blow up. I'm not talking about the convergence here. These guys may be really bad. This type of thing, this is called tadpoles. These are these looped edges. And where the end, both ends of the same edge and then the same vertex. And they're usually extremely badly behaved. Understand? So what kind of high terms? What will correspond to this? Well, there will be 4 copies of this x. There will be 4 copies of y. And again, one leg colored by z1, another by z2. So the graphs will be some things of the following sort. So let me give you a few examples of the graph which will appear there. So they will be like that. Z1, Z2, X, and Y. Again, what I do there again is the following. For each edge, say for Z1X, I write one of the terms of that sort. So here again there will be G of XX. Here there will be G of XY, etc. I write such products. And then I integrate over the positions of these internal vertices of X and Y, just as we did here for X. Now there will be a few more graphs now. So another interesting and nice graph is like that. Here again I have Z1, X, Y, Z2. Which will again contribute some product of 1, 2, 3, 4, 5 G's here. Here just the way it's described here by the graph, and then integrated over X and Y. So, etc. Now, again, what we should remember is that there is some graph, for instance, which will now look like that. See this graph. Or another graph, so, which will be, oh, okay, you know what, I already have it here, actually. I could already explain it here. So this graph did not enter. I forgot it, but I forgot it just before because it did not enter. And why? It's the same reason. So as I already said, for these vacuum diagrams, by which I mean some diagrams which contain a connected component of it, which is not path connected to any of these ends here, to the external ends, followed by Z1 and Z2, it disappears just because here we should normalize it by subdividing by ZU. And in this ZU, if I will write it, then in ZU there will be some term of that sort, just with this figure 8. It will be 1 plus this figure 8, plus more complicated, etc. So all these diagrams of that sort disappear, these vacuum diagrams, because of this normalization that I have to subdivide it by the ZQ. So do not appear. So in this in the fourth theory, the Feynman rules are like that. I am looking at, when I try to compute m-point function, like here there were 2-point function in this example, I will have 4 valent graphs with m external legs, which I mean univalent vertices. Univalent vertices, these legs, will be labeled by the points which appear here, Z1, Z2, etc., Zm. All the internal vertices will be labeled by some x, y, etc. And then we have to integrate over the positions of these points. And to each edge there corresponds a factor of g, of 2m. So that's basically how all these rules work. So now you can try with finding the sixth just to see what remains and what disappears. So, okay, now, unfortunately, so unfortunately, you know, I just recently understood that I'm taped. I cannot really give any joke. That's not the one which I would like.
This is the sentence, right?
Well, they call me chicken. Anyway, so
You can keep the tape.
so there's another problem in all this stuff, because usually theories which we consider, and at least many of the theories in which we're interested, these are gauge theories. And there the situation is more complicated. So if we have a gauge theory, so then what happens is the following. Then there is some group, say some group, oh, I already used capital G for this Green's function.
Just get your eraser. Better take your eraser.
So then I have some Lie group acting by symmetries on my space. So that I have my functional of this exponent and all the stuff. The action is preserved under the action of some group. So I have some orbits of my group. And then it's a real trouble. So some Lie group. So Lie group acts. Then I have, and it preserves preserving the action. That's fine. By which I mean, this quadratic part of potential. So then the things which were already badly behaved before become even worse. Now, why? Because now, when we make some integration, we also have to integrate over all the orbits here, and we have some integrals over some things of infinite volume, and of course everything will diverge very badly. So what people want to do in such a situation is to get rid of this unneeded, in a sense, integration over the orbits of this function. So what you would like to do is to take some section here, picking just one point at each orbit, and to look at your functional, at your action, only at these points, instead of integrating over also along the orbit. Okay? So this procedure of picking out the section is called gauge fixing. So, suppose so, well, maybe I should start with it more seriously, man. Okay. So let this be an L-dimensional Lie group. And I want to pick here, so these are orbits. Let me call it of G action. And we want to pick some section. Now, how can we do that? Well, what we can do is pick a function say f capital from, let me think that I work between R and D to R L such that it has only one zero on each orbit. Just 1, 0 on each orbit. And then we will plug the delta function of f, and consider now the old thing which we already had. So exponent d phi x minus half and taking out phi phi plus some potential u of phi. But now I will also multiply it by the delta function of f. So of f of phi. You know, let me just do the finite dimensional case. Yes, I already said that. Yeah. So I will let me return to finite dimensional. I will just explain. So sorry for the notations. I will just return to the finite dimensional case. This will be much simpler. So then in the finite dimensional case, my notations were v, these variables. Then there was v, t, a, v, the quadratic part. And then there was some u of v, potential. Sorry. So this will be a finite dimensional version. It will be rather clear in general. So here it's again, so they consider everywhere finite dimensional version, so there will be this.
So what is
Now,
L?
that's the trouble.
What is L?
Sorry?
What is L?
L is some L dimensional group.
Oh.
Okay, so I think about them as orbits being kind of L dimensional. D is the space of V. D is a coordinate function. Now, that's almost good, but not good enough. Why? Because we completely forgot about the volume of each orbit. So we really changed our function. So we would like to recover this volume of each orbit which we forgot. Now, we suppose already that this Lie group acts by isometries. So this change of volumes I can measure at each point, and particularly in zero. So there will be some determinant here standing for this change of volume. So how should I denote it? Well, I'll be rather sloppy. I'll denote it like F, E, G. Well, this thing is as follows. So I think that okay, I'll
What's the picture of what's right?
Hmm?
What's the picture of what's right?
I just want to see, now I do everything only in these points because of the delta function.
Well, it's supposed to be.
But
They made it slightly thicker than we thought.
yeah, okay. So you know, I had some huge orbits then, some were very small. And then again, some very big ones. So when I take a section here, it's kind of rather unfair that these ones, the big ones, enter with precisely the same weight as the small ones. I lost any information about the size of the orbit. So I would like to know, so why it happened? Because of this f. So I would like to know how much did f kind of shrink or pull, these volumes. I should take into account these volumes of the orbit. And if my action, so if this g acted isometrically, I can compute it just in the zero in points where f equals to 0. And as always, when I make some change of coordinates, some determinant of the change of the coordinates appears. So what is this?
Should you foliate the whole space by the fibers of f? And then you're integrating over the whole space. You're integrating over all the leaves. Since the functions are varying, you move the integral down to one level. When you move it, you have to pay with some determinant or something.
All right, yes. Yes,
I mean, that
yes, that's true. Yes.
I never understood this at all.
Yes, yes. Okay. Yes, that's true.
Is that right?
I think so.
Can you say it again then?
You're integrating over the whole space, so just fiber the whole space by the fibers of f, and just integrate over all the fibers. Integrate this way, but since the thing you're integrating is constant, when you apply the group, you can move the integral over this leaf
So
to
you
the
can
integral here. But when you move it, you have to pay with some Jacobian or something.
Just condition over
one leaf. Don't you mean integrate over one section?
Something.
Over one section, yes. So I integrate over the section where f.
Integrating over the whole space.
So instead of integrating over the whole foliated space, I just do it over the section where f vanishes.
Because the function is invariant, you
Yeah.
move the integral.
And then the Jacobian, of course, will appear.
Oh, now we know.
We don't know. Everything is very vague. If you want, you can think about compact, but it won't really help. So, what we try to understand is just the general, just try to forget about how rigorous are these things, because they're not. You cannot honestly write these functional integrals. So just try to take it easy. Yes, just look at it as some recipes, which sometimes, in the end, it sometimes makes sense, or at least it gives you a very good intuition to what should you do, what should be a combinatorial pattern. How should you try to define something? So just take it as something which should give you an intuition. If you feel better, then you can write compact.
So you integrate over RD.
Hmm?
You integrate over RD, yes?
Yes, here I integrate over RD, but you see here I have this thing,
Exactly.
which will kill a lot.
But this is measure zero set usually.
Hmm?
This is measure zero set usually. Of zero from f.
Here we go again.
No, but think of the delta function as just being a sharp Gaussian.
If you want, yes, just think that it's very sharp. It's not really delta, but it's all just has a huge peak near zero, and everything else almost does not count. So then, well, so suppose we have something of that sort. So what are the two new features? I have the same exponent. Then I have two new terms. I have some delta function, and I have the determinant. And we would like to present it as some change of the Lagrangian. So I would like to lift all these terms up inside the exponent, to squeeze them somehow in the exponent, right? To say that just my Lagrangian changed. Now, how can it be done? Now, it's relatively easy with these guys. So I can write it as an exponent in the following way. I will just write delta of f of v as the integral of, that should be some 2pi power n. By the way, it's Fourier transform, so it will be d psi, where psi is now, well, by which I understand the product here of d psi I from 1 to L. So it will be integration of L-dimensional space, exponent of I psi T F. So I can write this delta function as the exponent of something, which will give me some additional to my initial Lagrangian. So by the price of what? By the price of integrating over more variables, but this is not big. But it's much worse with these determinants. So this addition to the Lagrangian, if I would put it now, if I would add it already, here, this term would be called gauge fixed. Gauge fixing is just this choice of the section.
I'd still like to have a philosophical picture of what this step is supposed to be. I suggested something that I'm not sure is right. So
I don't think I can do it. I mean, already Stavros wanted from me to talk about that.
Whether it's a group
No, but-
or whether I don't know what that is supposed to be. If everything were in project and everything made sense, are you actually computing the whole interval, recomputing it in a different way? Or are you sort of saying, since, the group is infinite in this direction, I really am going to ignore that and just take it. And for this democratic reason, I put in this determinant, but that's just my heart.
That would be more my feeling, but I'm not the best person
Marty?
here. Maybe
Yeah, Marty.
Dirk.
Yeah. Okay, well, tell me. Let's stand up and tell us.
I think the correct way to interpret it is saying that we really wanted to do the integral on the orbit space, on that quotient space.
Oh, on the
Yeah.
orbit space.
But we don't know how to do that. We can't find global coordinates. So instead we use this section. And this
Wait, the phrase, no, that's too
No, but
suggestive. Do the
because
integral on the
the
orbit
question
space.
of
What does
the-
that mean?
we would
What-
really like to integrate. We would like to treat the orbits as work on the quotient space. Everything is invariant with respect to this action. So everything should in principle be defined on
Oh,
this
there should be
quotient
a
space.
reduced measure of the quotient space.
Exactly.
And
And that determinant essentially tells us.
Usually that's
Okay,
what it is.
now I know
But
that's
then,
supposed to be fine.
but then still you would like to.
That comes because F.
Yeah, everything is,
Because when we choose the local section,
Yeah,
we
okay.
can have an angle to the orbit and
Yes,
so on.
it
So that's what
That's
that's
right. Yeah. It really distorts the picture.
on the orbit space.
Yeah. Usually, say in Chern silence, the initial space would be the space of all connections. But then you wouldn't like to do that.
So
You
when I
would
say-
like to look at connections modulo gauge transformations. Just look at the modulo space.
So when I
But-
stood up and said yes, it's something completely wrong. You're
But-
not trying to integrate over the whole space. Really think of the orbit space as represented by a section. You have to do it.
Yeah, okay. Yes, but still, we would like to put this in because,
We need that.
my choice of F
Yeah, right,
was
you need that.
indeed,
The
yes,
section is like this.
Exactly.
yes,
Right.
because, okay, yeah, that's,
That's just the embedding of the quotient.
Yeah,
The section.
right,
Into
right.
the
The
section.
second
Yeah.
And when you do
is,
that, you,
Yes.
as was said,
Right.
one wants to use the volume element of the quotient.
right,
But
right.
here, one is naively using
Okay.
the volume element of the section, so you have to correct it by that.
Okay, now I have it.
I'm also. So it is much easier to deal with these delta functions than with these determinants. So to put this determinant, to squeeze it inside here in the exponent, is not really easy. So, if you would just do Gaussian integrals, then it would lead to some determinants, but unfortunately they all would be in the denominator. So here the way to deal with this is to introduce some new variables which are anti-commuting variables and which are called Gauss anti-Gauss, Polyak.
Cross-mod variables.
So,
Grassman numbers.
Cross-mod numbers over.
Grassmann number. So we should, to deal with this thing, we should introduce some anti-commuting variables. So introduce anti-commuting variables C bar and C. There are L of these and L of these. And these are L-dimensional guys. And so-called cost.
They're like fields that don't really exist. Well, that's why they call those.
So this seems to me that you don't understand something and then you do something even more complicated? Or?
But it works, you know. The amazing thing in all these computations that they really work in here.
Are we in hyperspace yet?
No, we're not invisible.
Yes,
I mean, as rigorous path-integrals, of course, there's serious problems in defining it. As a mnemonic tool for encoding complicated combinatoric rules of graphs, these are perfectly rigorous. There's nothing wrong with them, nothing ill-defined. Okay?
Good.
so you should just, you know, forget in the beginning about the path integrals and think about the recipe which it gives us. These recipes are often pretty good. You know, you sum over graphs of such and such type with such and such propagators, you know. And these guys already make much more sense. So here it will be now worse. So be prepared. Well, maybe I shouldn't talk about it too much. So, because you see, these are anti-commuting variables, and they have to do some integration over. So that's this. There are some reasonable rules of integration
Well, we had another
over these anti-commuting variables. Okay, so what is important for me that are some rules of integration. Just in such a way that for any well, let me write this now as lambda. Maybe I will just denote it by some lambda. Right? Then the determinant of lambda I can write as integral of dc bar dc element of c bar. So it's c bar. Okay. So just as before, I was looking at the quadratic part here. So it's something very similar to the usual Gaussian integral. Only now these guys, they're slightly different. And they're anti-commuting. But, so in a sense it is Gaussian integral, but with these anti-commuting variables. But what is nice that it gives you the determinant in the enumerator.
This is an algebraic construction.
Yes.
Yes.
Yes. Mathematically, I think it was developed by Berezin, and then some things about the integration, there were several other people working. Because integration turned out.
Why do you want to get that into the X so badly?
They should continue the same rules.
Because we want to write everything as the integral of some exponent. And this will be some new action in here. I want to like it as some change of the Lagrangian. I don't want to leave them downstairs.
So changes the quadratic term, right?
Yes, so it gives you an addition to this quadratic term. So the total will look like that. So the total will look like dv d sine dc bar dc. I have many new variables now. These guys are anti-commuting, these are usual variables. And then I have in the exponent, I just tried the old things, and then I added some new ones. So minus
Something
half
came as a flexible finish, I can keep the numbers very
dT A plus this whatever I had before, this potential u3, and then plus these two new terms. So one will be this sine t f3, and then there will be the last one, which is this ghost. So this new thing appeared because of the gauge fixing. And this appeared because of the ghosts. So again, this gauge fixing just means that we picked some kind of slice, some kind of section. But we ruined all the gauge invariants and everything, and maybe we picked it badly, so we have to compensate by remembering the information, by keeping this Jacobian, and this leads to these ghosts.
So you're going to regard this last term as part of the quadratic part, and these two little terms.
Yes. So what will it give us in the Feynman rules? Well, it will do the following. So remember, where did this A, or rather A inverse, appear? It appeared when I looked at the edges of my graph. Right? So to each edge, that corresponds some A inverse of this edge. And this potential led to some vertices. Some vertices, this was this U. So now these what will they do? So first of all, here I have a term which is very clearly quadratic. So it should play the same role as A. So we should put this lambda inverse on some edges. So we need some new type of edges. So if these, so the edges, as I said, they're called propagators usually. So this is called the gauge propagator. But then we introduce some other new type of vertices, dashed or dotted or whatever, some new edges, which are called the ghost propagator. And on each such, so there will be these ghosts. So just graphs with two types of edges. So one type of edges, another type of edges, and here we should put lambda inverse of the on each such ghost edge. Now we still did not incorporate these guys, but they play the same role in a sense as the potential. So there will be some new vertices, right? But these two types of edges should somehow interact. So there will be some vertices where there will be some kind of guys like that, and these will correspond to this term. This something which comes from this.
Are there vertices with only ghost propagators?
So these ghosts, I should be slightly more careful about this. So these ghost propagators, I should think about them as, say, being oriented, and they are non-symmetric. Before my form here, it was symmetric. I didn't care about the direction of this edge. Here, these guys are already non-symmetric. I have to orient them. And then there are some rules. There are only special types of vertices, just as before, say, in phi cube, we've seen only trivalent vertices. So here I will also have only some special type of vertices. So I can give an example, not more than that. So I see, yeah.
I think there are two important elaborations of what you said that you shouldn't miss. One is that lambda, when you say lambda inverse, you really don't mean lambda inverse. You mean the quadratic part of it. Lambda in general is V dependent, and that, otherwise it would be totally irrelevant. It would just decouple.
Yes.
So
yes.
you need the V dependent, and that gives you vertices. The other important thing is the A. The reason we had to do all this was because A has a kernel, and you can't invert it. And once the quadratic part of the psi f term fixes that, so you have part of it goes into correcting the propagator, the gauge propagator.
So both. So lambda, this thing is not really quadratic. Okay, this thing in general is not kind of constant, right? Independent. So if I want to be careful, I should really say that here I use only the quadratic approximation. But when I say about lambda inverse. So it's only of the quadratic part. Now, with A, when I said here A inverse of the H, I was, of course, again sloppy. The whole reason why we started it was the following. So, how did we manage before? Before, we said, well, by the stationary point method, by the stationary phase method, I should look just somewhere near the critical point of my action, and there I see the quadratic term, etc. Now, so now what happens is that these critical points are not isolated anymore because there's some group, the gauge action. Yeah. So what I see is something of this sort. So
that's the gauge.
yes, because of the gauge group, right? They're not isolated anymore, and this was the source of our problem. That's why we wanted to take these slices, to take these sections. So of course my A in the beginning just meant that it was degenerate. It had some current. So here when I say A inverse of the H, it's again sloppy. I should be more careful about saying what I should do here.
So the lambda inverse of the quadratic part.
They in a sense compensate for, yes, they correct these problems.
Okay, very good. Okay. That's the story. That's the story with all these areas.
You know, it's pretty simple. You just take the quadratic part of the psi f term.
Yeah.
Okay, that has a piece linear in psi and linear in v times some matrix. Now in this bigger space of v and psi, that operator is invertible. That doesn't have a term. And so that's what replaces A. You have to think of psi as an extra component of V. Extra piece of V.
You move the,
So I love, yeah.
you group the third term and the first term together to make it, and that's your new A. You add an A in it.
Right.
Well, yeah.
First and third. Right?
Somehow, yes.
That's what he's saying. And that quadratic form is vertical of the base.
Yeah.
Now it's
Basically,
fixed.
it's better, yes, it's better than it was. So, in any case, so, in each given example, you usually can manage to do all this. The procedure now already depends on a good choice of your gauge fixed, the way you fix the gauge. And there's quite some choice involved. At the moment you've done it, and you've done it well, then you arrive to some quite reasonable type of Feynman diagrams, Feynman rules, where you have two types of propagators. These propagators are more tricky, so you see something of that sort. There are some graphs with directed agent equations. These mixed vertices, etc. But it's still manageable. And what one can try to do in particular is, and that's how many mathematicians do nowadays, is just to forget all this long path which led you there, and just try to use these recipe, as a recipe for a rigorous mathematical construction of something. Well, this will be my last lecture. How using some rules in Chern-Simons or in, say, open strings on a disk, how you can purely mathematically after that just forget all these things which you can consider as a motivation, and just using these Feynman rules construct rigorous mathematical objects. So sorry, it was